This video is for Chemistry in the Earth System, Unit 1.3, the cycling of matter and energy. Today's essential question is, how do energy and matter interact as they cycle through Earth's systems? Hello, baby birds! Today we'll explore how energy and matter move through Earth's systems in predictable, interconnected cycles. We'll use an anchoring event, the Maori navigation, using ocean currents and winds to make these ideas concrete. Polynesian and Maori navigators read winds, swells, clouds, stars, and bird patterns to cross vast ocean distances without instrumentation. As we study each cycle, ask what signs in the air, water, rocks, and living world would a navigator notice? Earth is mostly a closed system for matter, meaning that atoms cycle but don't arrive or leave in any large amounts. But it's an open system for energy, mainly from the sun, plus Earth's interior. Energy flow drives motion. Matter cycles along the atmosphere, hydrosphere, geosphere, and biosphere. Maori navigation relies on the regularity of these flows. Seasonal sun paths influence wind belts and rainfall, which then affect swell patterns and travel windows. As we go along, note where energy drives a process and where matter changes form and location. Matter, which is anything with mass and volume. Matter exists as solid, liquid, or gas. Adding or removing energy changes the state of that matter. Melting, evaporation, condensation, freezing, sublimation, deposition. Energy cannot be created or destroyed, only transformed. We call this conservation of energy. Most surface processes are solar powered. Some, like volcanism, are powered by Earth's interior. Now, here is a common misconception. Energy is not matter. Sunlight, which is electromagnetic radiation, carries energy but has no mass. This distinction is crucial when we track how energy moves through systems while matter cycles within them. Thermal energy is the total microscopic kinetic energy of particles, the internal motion that shows up as temperature. Nuclear energy comes from changes in atomic nuclei. The sun's nuclear fusion provides the steady energy input that powers photosynthesis, weather, and ocean circulation. Radioactive decay and residual heat inside Earth drive geothermal energy and plate motion. Navigators timed voyages with seasonal changes in solar heating because they alter winds, clouds, and ocean conditions. Two processes, fission, which is the splitting of heavy nuclei and releases energy, occurs in Earth's interior and in nuclear power plants, as well as fusion, which is the combining of light nuclei. This powers the sun and converts a tiny bit of mass into a lot of energy. Solar fusion energy arrives as light and heat, driving all surface cycles, winds, currents, and life. Students often mix up fission and fusion. Remember, fuse means to join, like in fusion, and fission, like a fissure, means to split. Thermal energy transfers by radiation, conduction, and convection. Remember, radiation is energy traveling as electromagnetic waves. Short-wave solar radiation heats Earth, and Earth emits long-wave radiation back into space, preventing runaway heating. Conduction is the direct particle-to-particle transfer of heat. An example is hot magma conducts heat into the surrounding rocks. And then convection. Warm, less dense fluid will rise, and cooler, denser fluid sinks, forming what we call convection cells in the atmospheres, also oceans, and even Earth's mantle. Because remember, the asthenosphere flows. Because Earth is tilted 23.5 degrees and is curved, sunlight is uneven. Direct and concentrated near the equator, but oblique near the poles. Land heats or cools faster than water, and the result? Global pressure bands. The equator low at 30 degrees, high at 60 degrees, equator low, 30 degrees high, 60 degrees low, and 90 degrees high. Wind belts and ocean currents that redistribute heat. Ocean currents are not caused by tides. They primarily are driven by winds, Earth rotation, density differences, and continental deflections. Water moves among ocean, atmosphere, and land via evaporation, condensation, precipitation, infiltration, and runoff. Each phase change requires adding or removing energy. Warm seas boost evaporation. Rising air cools and condenses into clouds. That precipitation returns water to the surface and groundwater. There is no true beginning or end to a cycle, specifically the rock cycle. For igneous rock, this is when magma or lava cools and then solidifies. We have sedimentary rock, which involves weathering. This weathering creates sediments. That sediment then deposits or goes through deposition and then goes into compaction or cementation. Then we have metamorphic rock. This is when existing rock, altered by heat and pressure, can melt and start over. Geochemical cycles move elements between living things and the physical environment. Some key cycles here: the carbon cycle, the phosphorus cycle, and nitrogen cycle, as well as the water cycle, which is often talked about. But these cycles do not merge into one giant cycle. Each cycles independently, but they can influence each other. Carbon reservoirs can be found in the atmosphere, terrestrial biosphere, oceans, and sediments and rocks. In the air, mainly in the form of CO2 and some carbon monoxide. In the oceans, dissolved as carbonic acid, which is H2CO3. Bicarbonate, which is HCO3 minus, it's an ion, and then carbonate, which is also an ion, CO3 with a 2 minus charge. We also see carbon reservoirs on land. We have calcium carbonate, CaCO3, in rocks, carbon in biomass as well as soils. We also see carbon moving. For example, photosynthesis pulls CO2 into biomass from the atmosphere. Respiration and decomposition return that CO2, and some carbon is locked into rocks. For example, shells like limestone for millions of years. Photosynthesis. Now, for photosynthesis, we have a balanced chemical equation. 6 CO2s plus 6 H2Os plus light react to form glucose, which is C6H12O6, and 6 O2s. This is a step-by-step process. Sunlight is going to be absorbed by pigments, for example, chlorophyll, and that sunlight provides energy. Step 2, the CO2 and H2O are rearranged into glucose, where the stored chemical energy will be found, and O2. Step 3, the ratio of 6 to 6 to 1 to 6 coefficients keep atoms balanced, meaning there's a conservation of matter. But not only green plants photosynthesize. Certain algae and bacteria do also, using various pigments, green, brown, or even red. But we also have the opposite of this. We have respiration. Again, we have the glucose, C6H12O6, plus 6 O2s, reacting to form 6 CO2s plus 6 H2Os and energy. Organisms will break down that glucose to power certain life processes, returning CO2 and H2O. Let's talk about residence time. This is how long, on average, a particle stays in a reservoir, meaning it stays stored. The formula is T is equal to big V over little v. Big V is the amount in the reservoir. Little v is the rate of input or output. We can work out certain examples, which we'll in class. But suppose an atmospheric carbon reservoir has a big V of 800 gigatons of carbon. Annual net outflow to the ocean and biosphere is little v is equal to 8 gigatons of carbon per year. If we want to compute the residence time, again, T is equal to big V over little v, that's going to be 800 divided by 8, which is equal to 100 years. So what does this mean? Carbon atoms, according to this calculation, on average remain 100 years in the atmosphere before moving into another reservoir. Systems co-evolve and influence each other. For example, the biosphere and the atmosphere. Oxygen from photosynthesis enabled animal evolution. Plants draw down CO2 and influence the climate. We also see the biosphere interacting with the geosphere when we see microbes help form soils and support land plants. Coral reefs alter coastal erosion and deposition and create habitats. We also see the hydrosphere interacting with the atmosphere, in which we see evaporation and condensation link water and energy cycles. When we look at greenhouse gases, we see CO2. We also see CO2 traps outgoing long-wave radiation, which warms the lower atmosphere. Impacts of this include the water cycle, higher evaporation, more atmospheric moisture, and there's a shift toward more rain than snow in many regions. That means an altered precipitation pattern. In ocean circulation, fresh water from melting ice can influence the thermohaline circulation, changing global heat distribution. We also see the carbon cycle, increased atmospheric CO2 and reduced carbon storage from deforestation. We also see biodiversity and feedbacks. Ecosystems adjust or stress. Nutrient cycling and food webs shift. At this point, you should be able to generate a full and appropriate response to today's essential question. How do energy and matter interact as they cycle through Earth's systems?